Okay, so we're on to the last two questions of the second, or of the sixth chapter of Statistical Rethinking, second edition, 6H6 and 6H7. So if you're going to use any of this code, make sure that you've installed and loaded the rethinking package with those first two code blocks. And let's get into it. Where are we? Okay, so for 6H6, I'm almost there, 6H6, we want to consider a research question of our own devising, so we're all going to have different answers here, and then draw a DAG to represent it. And then we want to kind of pick apart that DAG and, as though we were seeing a colleague's model and try to find weaknesses. Okay. So my setup here is going to be that, that I have a particular toxin that causes fever, F, which really should be body temperature, but I've just used T for toxin. And that effect is mediated by a cell type called C, right? So if we had more of these cells, then maybe there's more of a robust fever response, or that's the hypothesis, okay? So if I'm going to draw that DAG, it looks like this, T, C, F, okay? We can start to pick this apart. So a colleague might come along and say, well, what if there is just a genetic disposition for the number of cells that an animal has, and that genetic disposition also affects body temperature, okay? And it might look something like this, okay? Well, actually, before saying that, so if I want to test the hypothesis that C is the mediator to the effect of T on F, then I'm going to have to regress T and C, right? I'm going to have to regress F on T and C, all right? But if there is some other maybe genetic predisposition or whatever that is also impinging on C, then by having both T and C in the model, I am opening up this non-causal path from T to F, right? And so in this case, regressing on C is a disaster. And this is a theme when you're trying to do kind of this mediator analysis. Because you don't know what the system truly is, you are really risking all sorts of hazards by regressing on mediators. But nevertheless, we'll march forward. There's also the possibility that there's some other physiological mechanism that both G and T can impinge on, okay? And there's also the possibility that the toxin itself has other mechanisms not mediated by C that affect fever. All of these are possibilities, okay? But we're just marching ahead here with our basic model, okay? We're going to want to test this, and so one way that we can look for tests is to use the implied conditional independencies, and like we've already said, F is independent of T given C, okay? And we already saw that. F is independent of T given C, all right? And so that means that to test this, we're going to regress the mean of F on an intercept, as well as temperature, or I'm sorry, toxin, and number of cells, okay? So that's it for 6H6, and now we're actually going to start building some regression models to test this and to kind of poke at our DAG and our hypothesis. So before doing that, I think it's important to kind of really make clear what we're trying to do when we're running these simulations, right? So we're going to simulate some data and then deploy a model on that data, that fake data, to make sure that our model is capable of detecting the kind of effect we think that there is, okay? So our intention here is to, again, figure out, so on the assumption that the system under study actually conforms to our hypothesis, we want a model that can detect the interesting things of that supposed system, okay? So that means that we're going to make some fake data and deploy a model for that fake data. And if the model is able to perform correctly on that fake data, then we will move on and deploy it on empirical data that we've collected. But that does not mean that the model is competent for the empirical data, right? It's only competent if the actual system under study conforms to our assumptions, to our hypothesis, right? It could be that even though our model performs great on our fake data, right, that the real world is not built in the way that we've made the fake data, right? And so that does not automatically mean that just because a model passes the test on the fake data does not necessarily mean that its results, that its outcomes when you employ it on empirical data are accurate. It's accurate insofar as you've made correct assumptions. Okay, that's a big thing. So there's kind of a Popperian feel to this, right? Where we can't really prove that any of our statistical models is a good fit to the empirical data, but we can certainly show that a model is not a good fit to empirical data insofar as the empirical data conforms to our assumptions. So that's kind of a mouthful, but anyway. Okay, so remember, we want to build a model like this, and so first we need to create some data that conforms to this. All right, and so I'm going to have I've built the data here. Okay, so I'm going to have 25 data points in 2 different conditions. Right, so 2 conditions are both going to have 25 data points. Okay, so for a total of 50 data points. Okay, and some of these are going to have a toxin. Okay, where toxin is 0, and some where toxin is 1. So no toxin or toxin. I'm going to have cells. Right, these different animals are going to have some number of cells, and they're going to have an average of 1,000 cells plus or minus some standard deviation. And then fever, or body temperature really, is going to start at an average of 98.6 degrees Fahrenheit, and it will be increased or decreased according to T and C. Right, so when T is present, this term here will be about 2, right, normalized to cell types. But when no toxin is delivered, then this will just drop out, and the value should be just the 98.6 plus or minus some standard deviation. Okay, so I wrap all that together in a data frame, and we can just kind of look at a few of those entries. Okay, so again, I have toxin. These animals are not getting toxin. These animals are. Here is the cell number across these different animals. And then here is the body temperature across these different treatments. Okay, for these different animals. Okay. All right. So we're going to start building our statistical models, and so for the first one, we are going to regress F on just T. Right, the effect of F on T is just going to show the effect of T on F, ignoring C here, right? It's just gonna be that whole loop there, okay? Unimpeded by by conditioning on C. All right. So I run this, and this is what I get. Okay. So it's about as we expected. Okay. So the effect of T on F, toxin on fever, is about what we expect. Kind of approaching 2. Well, so that's fine. But that's not really the interesting regression. The interesting one is now what happens when we regress on C. Okay, and remember that we're expecting that if I regress on C, then the beta coefficient for T on F is going to go to 0, and all of that effect, or most of that effect, is going to be absorbed by the effect of C on F. All right. And so that's what we have here, right? So we have T and C now being regressed, okay? And what do we see? We see nothing different, okay? Or basically nothing different, all right? And in fact, we see that the effect of we see that the effect of C on F is 0. Okay, so what's going on here? Well, what's going on here was a misunderstanding at the very beginning of our DAG. Okay, so here's our DAG, and the assumption that we're making that is incorrect is that cell number is being affected by toxin. right? But our data is not a function of t at all, right? So what's going on is that even though it is true that the effects of the toxin are mediated by these cells, right, onto fever, our model is not picking it up. Why is it not picking it up? So remember that these edges here, these links between the nodes, are really covariation. That means if I could adjust the value of t, I should expect to see differences in the value of c. Now, I call that a cause and effect based on outside knowledge, right? The direction of the arrow is really an assumption that I'm making, okay? But again, c is not covarying with t at all, okay? So this DAG is not appropriate for the actual system, at least not the data that we've created, okay? So I hope that this kind of highlights why it's really critical to run simulated data to check your understanding of everything and to make sure that your model really is modeling the thing that you think that it's modeling, okay? So again, even though it is true that fever is a function of both T and C, because C is not affected by T, I've used an inappropriate DAG, I've used an inappropriate regression, and my regression cannot find the mediating effect of T to F, even though it does exist in the system that we're studying, okay? So anyway, I hope that was helpful. That was the surprise ending. Anyway, we are on to Chapter 7 next time. Okay, thanks.